Whether to treat the UPS as a separately derived system depends on its specific design and installation characteristics. Factors to consider include the type of transformer, isolation, and independent grounding. The UPS is a built-in transformer, which is an essential component for isolating the secondary circuit from the primary circuit. The transformer's isolation rating determines the level of electrical isolation between the primary and secondary circuits. A high isolation rating indicates a well-isolated system. The UPS should have its own dedicated grounding system, separate from the building electrical system. The National Electrical Code, NEC, defines a separately derived system as a system that originates from a transformer or other device that provides isolation from the primary circuit. The NEC requires that separately derived systems have their own grounding electrode system. Based on the limited information provided, it is recommended to treat the UPS as a separately derived system. This is because the UPS has a built-in transformer, which provides electrical isolation, and the UPS should have its own dedicated grounding system. Treating the UPS as a separately derived system will ensure that it meets NEC requirements and provides the necessary level of safety and protection. Since the UPS is treated as a separately derived system, the Y side should not be connected to the building steel. The Y side of the transformer should be grounded to the dedicated grounding electrode system of the UPS. Additional considerations: firstly, the UPS should be installed in accordance with the manufacturer's instructions and applicable electrical codes. Secondly, regular maintenance and testing should be performed to ensure the proper operation and safety of the UPS system. Thirdly, consult with a qualified electrician to verify the specific requirements for your installation. The National Electrical Code, in section 250.30, A1, provides specific requirements for grounding separately derived alternating current systems. This section mandates that a grounding electrode conductor must connect the grounded conductor of the separately derived system to a grounding electrode. The size of this grounding electrode conductor is determined by NEC Table 250.102. C1, based on the size of the derived and grounded conductors. For example, if the ungrounded conductors are size 3/0 or smaller copper, the grounding electrode conductor must be at least size 8 copper. Furthermore, the grounding electrode itself must meet the requirements outlined in NEC section 250.52, which covers various types of acceptable grounding electrodes, such as metal water pipes, metal building frames, and ground rods. The connection to the grounding electrode should be made in accordance with NEC section 250.68, ensuring a reliable and permanent connection. NEC section 450.3 provides guidelines on transformer overcurrent protection. This section details how to properly protect transformers from overcurrent conditions, which can prevent damage to the transformer and the connected equipment. The primary side of the transformer typically requires overcurrent protection sized at no more than 125% of the transformer's rated primary current, as specified in NEC Table 450.3. For example, if a 480 volts to 120 volts/208 volts transformer is rated at 80 kilovolt amps, the primary current can be calculated as 80,000 divided by 480 volts, divided by the square root of 3, which equals approximately 96.2 amps. Thus, the overcurrent protection should not exceed 125% of 96.2 amps, which is approximately 120.25 amps. Therefore, a 125 amps breaker or fuse would be appropriate. On the secondary side, the overcurrent protection must comply with NEC section 240.4, which addresses protection of conductors. The conductors must be protected against overcurrent in accordance with their ampacity ratings. If the secondary conductors are rated at, say, 400 amps, then the overcurrent protection should not exceed 400 amps. NEC Article 700 covers emergency systems. This article is relevant if the UPS is intended to provide power to emergency circuits during a power outage. Emergency systems require specific wiring methods and overcurrent protection to ensure reliability. The wiring for emergency circuits must be kept independent of other wiring, as specified in NEC section 700.9. The overcurrent protection for emergency circuits must be selectively coordinated to minimize outages, as described in NEC section 700.27. Selective coordination ensures that only the affected circuit trips during a fault, while other emergency circuits remain operational. NEC Article 701 pertains to legally required standby systems. These systems are required by law to supply power to specific loads, such as fire pumps or ventilation systems in hazardous locations. Legally required standby systems must also comply with specific wiring and overcurrent protection requirements. The transfer equipment for these systems must be designed to prevent inadvertent interconnection of normal and standby sources, as stated in NEC section 701.6. This ensures that the standby system operates independently from the normal power source to prevent backfeed and potential hazards. NEC Article 702 addresses optional standby systems. These systems provide power to non-essential loads during a power outage, such as convenience outlets or HVAC systems. While not legally required, these systems must still be installed in accordance with NEC guidelines to ensure safety. The generator supplying the optional standby system must have adequate capacity to handle the connected loads, as specified in NEC section 702.5. The transfer equipment should be suitable for the intended application and must be properly labeled, as described in NEC section 702.7. NEC section 250.20 outlines the requirements for alternating current systems to be grounded. This section mandates that systems operating at 50 volts to 1000 volts that supply premises wiring must be grounded under certain conditions. These conditions include systems where the neutral conductor is used as a circuit conductor, systems where the voltage to ground does not exceed 150 volts, and three-phase, four-wire systems. The purpose of grounding is to limit voltage surges due to lightning or unintentional contact with higher voltage lines and to stabilize the voltage to ground during normal operation. NEC section 250.24 provides guidelines for grounding separately derived alternating current systems. This section specifies that the grounding electrode conductor must be connected to the grounded conductor of the separately derived system at a single point. This connection should be made at the source of the separately derived system, such as the transformer. The grounding electrode conductor must be sized according to NEC Table 250.102. C1, based on the size of the derived and grounded conductors. NEC section 250.30 further details the requirements for grounding electrode systems for separately derived systems. The grounding electrode system must consist of one or more grounding electrodes that meet the requirements of NEC section 250.52. Acceptable grounding electrodes include metal water pipes, metal building frames, and ground rods. The grounding electrode conductor must be connected to the grounding electrode in accordance with NEC section 250.68, ensuring a reliable and permanent connection. NEC section 250.50 covers the requirements for grounding electrode systems in general. This section mandates that all available grounding electrodes must be bonded together to form a single grounding electrode system. This bonding ensures that all grounding electrodes are at the same potential, minimizing the risk of voltage differences and improving the effectiveness of the grounding system. The bonding jumpers must be sized according to NEC Table 250.66, based on the size of the largest ungrounded conductor. NEC section 250.64 provides guidelines for the installation of grounding electrode conductors. This section specifies that grounding electrode conductors must be securely fastened to the surface on which they are carried and must be protected from physical damage. The grounding electrode conductor must be continuous and without splices or joints unless specifically permitted by the NEC. The conductor must be installed in a manner that minimizes the risk of damage and ensures a reliable grounding connection. NEC section 250.104 addresses the bonding of metal water piping systems. This section requires that metal water piping systems that are likely to be energized must be bonded to the service equipment enclosure. the grounded conductor, the service, the grounding electrode conductor, or the grounding electrode. The bonding jumper must be sized according to NEC Table 250.102 C1 based on the size of the service entrance conductors. The bonding ensures that the metal water piping system is at the same potential as the electrical system, reducing the risk of electric shock. NEC Section 250.118 lists the types of equipment grounding conductors that are permitted by the NEC. These include copper, aluminum, or copper-clad aluminum conductors, rigid metal conduit, intermediate metal conduit, electrical metallic tubing, and flexible metal conduit under certain conditions. The equipment grounding conductor must be installed in the same raceway or cable as the circuit conductors and must be sized according to NEC Table 250.122 based on the rating of the overcurrent protected device. NEC Section 250.122 provides guidelines for sizing equipment grounding conductors. This section specifies that equipment grounding conductors must be sized based on the rating of the overcurrent protective device protecting the circuit. The equipment grounding conductor must be large enough to safely carry the fault current back to the source, allowing the overcurrent protective device to trip and clear the fault. NEC Table 250.122 provides the minimum size of the equipment grounding conductor for various overcurrent device ratings. For example, for a 20 amps overcurrent device, the minimum size of the equipment grounding conductor is 12 American wire gauge copper. NEC Section 300.3 addresses the general requirements for wiring methods. This section specifies that all conductors of a circuit, including the equipment grounding conductor, must be installed in the same raceway or cable. This ensures that the impedance of the ground fault current path is low, facilitating the rapid tripping of the overcurrent protective device. The wiring method must be suitable for the environment in which it is installed, considering factors such as temperature, moisture, and physical damage. NEC Section 310.15 provides guidelines for the ampacity of conductors. This section details how to determine the allowable current carrying capacity of conductors based on factors such as conductor size, insulation type, ambient temperature, and the number of conductors in a raceway. The ampacity of the conductor must be sufficient to carry the load current without exceeding the conductor's temperature rating. Correction factors and adjustment factors must be applied as necessary to account for ambient temperature and the number of conductors in a raceway. NEC Table 310.16 provides ampacity ratings for various conductor sizes and insulation types. For example, a 12 American wire gauge copper conductor with THHN insulation has an ampacity of 30 amps at an ambient temperature of 30 degrees Celsius. However, this ampacity must be adjusted if the ambient temperature is higher than 30 degrees Celsius or if there are more than 3 current-carrying conductors in a raceway. NEC Section 408.3 addresses the overcurrent protection requirements for panel boards. This section specifies that panel boards must be protected by overcurrent devices with a rating not greater than the panel board's rating. The overcurrent devices must be readily accessible and must be located in a manner that prevents tampering. The panel board must be properly labeled to indicate its voltage current rating and the number of phases. NEC Section 430.52 provides guidelines for motor overcurrent protection. This section details how to protect motors from overcurrent conditions such as short circuits and overloads. The overcurrent protective device must be sized based on the motor's full load current rating and the motor's design characteristics. Different types of motors have different overcurrent protection requirements, as specified in NEC Table 430.52. For example, for a square cage induction motor with code letter F to V, the maximum rating of the overcurrent protective device is 250% of the motor's full load current. NEC Article 440 covers air conditioning and refrigeration equipment. This article provides specific requirements for the wiring and overcurrent protection of air conditioning and refrigeration equipment. The disconnecting means for air conditioning and refrigeration equipment must be readily accessible and must be located within sight of the equipment. The overcurrent protection must be sized based on the equipment's nameplate rating and the requirements of NEC Article 440. NEC Section 445.12 provides guidelines for the overcurrent protection of generators. This section specifies that generators must be protected by overcurrent devices with a rating not greater than 115% of the generator's nameplate current rating. The overcurrent devices must be located in a manner that prevents tampering and must be readily accessible. The generator must be properly labeled to indicate its voltage, current rating, and the number of phases. NEC Article 500 addresses hazardous locations. This article provides specific requirements for electrical equipment installed in hazardous locations, where flammable gases, vapors, or dust may be present. Equipment installed in hazardous locations must be specifically designed and certified for use in those locations. The wiring methods and overcurrent protection must also comply with the requirements of NEC Article 500. NEC Article 517 covers healthcare facilities. This article provides specific requirements for electrical equipment installed in healthcare facilities, such as hospitals and nursing homes. Healthcare facilities require reliable power and grounding systems to ensure patient safety. The wiring methods and overcurrent protection must comply with the requirements of NEC Article 517, which are designed to minimize the risk of electrical shock and fire. In conclusion, treating the UPS as a separately derived system and adhering to the NEC guidelines ensures a safe and compliant installation.